And here I have some good news for you. While you should definitely know what this is about, it will not be on the test. Okay. Okay. That doesn't mean that you should forget everything we've seen about it, okay? Now, what's next on my list of topics? So we've seen differentials. So remember, the differential of f, by definition, would be this kind of quantity. So at first, it looks just like a new way to package partial derivatives together into some new kind of object. Now, what is this good for? Well, it's a good way to remember approximation formulas. It's a good way to also study how variations in x, y, z relate to variations in f. In particular, we can divide this by variations actually by dx or by dy or by dz in any situation that we want to find, or by d of some other variable, to get chain rules. So the chain rule says, for example, well, there's many different situations, but for example, if x, y, and z depend on some other variable, say, other variables, maybe even u and v, then that means that f becomes a function of u and v. And then we can ask ourselves, how sensitive is f to the value of u? And, well, we can answer that. So the chain rule is something like this. And let me explain to you again where this comes from. So basically, what this quantity means is if we change u and keep v constant, what happens to the value of f? Well, why would the value of f change in the first place when f is just a function of x, y, z and not directly of u? Well, it changes because x, y, and z depend on u. So first we have to figure out how quickly x, y, and z change when we change u. Well, how quickly we do that is precisely partial x, partial u, partial y, partial u, partial z, partial u. These are the rates of change of x, y, z when we change u. And now, when we change x, y, and z, that causes f to change. How much does f change? Well, partial f, partial x tells us how quickly f changes if I just change x. So I get this. That's the change in f caused just by the fact that x changes when u changes. But then y also changes. Y changes at this rate, and that causes f to change at that rate. And z changes as well, and that causes f to change at that rate. And the effects add up together. Does that make sense? Okay. And so in particular, we can use the chain rule to do changes of variables. If we have, say, a function defined in terms of polar coordinates r and theta, and we'd like to switch it to rectangular coordinates x and y, then we can use chain rules to relate the partial derivatives. And finally, last but not least, we've seen how to deal with non-independent variables. So when our variables, say, x, y, z, are related by some equation. So one way we can deal with this is to solve for one of the variables and go back to two independent variables. But we can't always do that. Of course, on the exam, you can be sure that I will make sure that you cannot solve for the variable you want to remove, because that would be too easy. So then when we have to keep all of them but handle, take into account this relation, we've seen two useful methods. One of them is to find the minimum or the maximum of a function when the variables are not independent. And that's the method of Lagrange multipliers. So remember, to find the minimum or maximum of a function f subject to the constraint g equals constant, well, we write down equations that say that the gradient of f is actually proportional to the gradient of g. So there's a new variable here, lambda, the multiplier. And so, for example, if fg, well, I guess here I had functions of three variables, so this becomes three equations. F sub x equals lambda g sub x, f sub y equals lambda g sub y, and f sub z equals lambda g sub z. And when we plug in the formulas for f and g, well, we're left with three equations involving the four variables x, y, z, and lambda. What's wrong? Well, we don't have actually four independent variables. We also have this relation g equals, well, whatever the constraint was, relating x, y, and z together. So then we can try to solve this, and depending on situations, it's sometimes easy and sometimes it's very hard or even impossible. So in particular on the test, I haven't decided yet, but it could well be that the problem about Lagrange multipliers will just ask you to write the equations, not to solve them. Okay, so, well, I don't know yet. Okay, I'm not promising anything, but just, before you start solving, check whether the problem asks you to solve them or not. Okay, if it doesn't, then probably you shouldn't.